Hi, in this video we are going to discuss the behavior of the Fourier series coefficients for larger values of the magnitude of the index k. Now, first of all, we remember that if x of t is a periodic signal, so this is a periodic signal with a fundamental period capital T0, then x of t has the Fourier series representation in terms of this expression ak e to jk omega 0 t, and omega 0 is, as we remember, 2 pi over t0. Now, what can we say about the coefficients ak? For instance, we can look at the behavior of the coefficients for larger values of the magnitude of k, taking larger values, meaning that we are looking at the coefficients of the high frequency components in the Fourier series representation. So what can we say about the behavior of the coefficients of the high frequency components? Now we have the following result. In fact, it is a theorem, and we are going to see the proof of this theorem in this video as well. So, okay, let me write it as a theorem. Let x of t be a function over the interval which represents a period from t0 to t0 plus capital T0, which is absolutely integrable in the Riemann sense, then we have the following two results. Magnitude of ak is bounded for all k, and second, magnitude of ak tends to 0 as magnitude k tends to infinity. Okay, therefore we have this result. The condition given in the theorem is the following. The function is absolutely integrable over a period in the Riemann sense. Okay, we are talking about the periodic signals, of course. So this theorem is applicable to our periodic signals. Now we are going to see the proof of this theorem at the end of the video. But first of all, let us see some examples related to this result. For instance, let us consider the example of the periodic pulse train. So we have this, we have treated this example several times before. So we have P of t equal to a constant over the interval from minus t0 over 2 to t0 over 2, and the constant is equal to a. And we obtain the periodic signal x of t as the periodic extension of this pulse, p of t minus m t0. Okay, where we assume that t0 is greater than t0. So we have the periodic extension of this rectangular pulse, and we know that the Fourier series of x of t is ak e to j k omega 0 t, k from minus infinity to plus infinity. And here omega 0 is related to our fundamental period as in terms of this expression, 2 pi over capital T0 is equal to omega 0. And we know that AK is equal to A T0 over capital T0 sinc K T0 over capital T0. And let us remember the definition of the sinc function. It is sine K, in fact, we have pi K T over T0 divided by pi K T T0 over capital T0, T0 over capital T0. Now it is clear that for larger values of k, this sine function is of course bounded between minus 1 and plus 1. Therefore, for larger values of k, ak decreases as 1 over k. For larger values of k, values of magnitude of k, because k can take positive or negative values, ak is proportional to one over k, or it decreases as 1 over k, and it is clear that as k tends to plus or minus infinity, ak in magnitude tends to 0. Okay, so we have seen the an application of the theorem which tells us that if x of t is absolutely integrable in the Riemann sense over a period for periodic signals, the Fourier coefficients in magnitude are bounded for all k, and also magnitude of the Fourier coefficients tends to 0 as k tends to plus or minus infinity. Okay, now in order to understand the statement given in the theorem, let us see a certain example where we will see that the coefficients will not tend to 0 in magnitude as k tend to infinity. And remember that example is our well-known impulse train example. Okay, so we have x of t as the periodic impulse train, and from minus infinity to plus infinity, delta of t minus m t0. So it is the periodic impulse train with a fundamental period t0, and the Fourier coefficients in this case can be calculated as 1 over t0. Remember, we integrate over a period, for example, from minus t0 over 2 to t0 over 2, delta of t e to minus jk omega 0 t integrated with respect to t, and using the sampling property of the impulse, the coefficient ak turns out to be 1 over t0. Now here we observe that the Fourier coefficients are all constant for all k. Ak is equal to 1 over t0 for all k, from minus infinity to plus infinity. So in this case, we do not observe the decay behavior we have seen in the statement of the theorem. The reason is that here our signal is the impulse train, and remember the impulse, although we call it a function in the generalized sense, is not a well-behaved function. In fact, it's a singular mathematical entity, which is 0 for all values of t, except at the point where the impulse strikes, and there it is infinite in magnitude. So since the conditions of the theorem does not hold in this case, the coefficients ak do not exhibit such a decay behavior. In fact, if you look at the Fourier series, we have x of t equal to k from minus infinity to plus infinity, 1 over t0. These are the coefficients ak, e to jk omega 0 t. We can also claim that this series is not convergent, which is expected because of the singular behavior of the impulse signal. Okay, therefore, in this case, we do not even have convergence of the Fourier series. Okay, now let us see another example. With these two examples in mind, we can now discuss the following example. Okay, but maybe before continuing with that example, here we can just note that we do not observe the decay behavior of the coefficients of the Fourier series for this specific case, and the reason is that the signal or function, the periodic function defined in this or given in this example, does not satisfy the conditions given in the theorem. Now, let us see the following example. Let us define the pulse P of t as the triangular pulse, which is non-zero from minus t0 over 2 to t0 over 2, and its value at t equal to 0 is equal to a. Okay, and we obtain a periodic signal x of t in terms of this triangular pulse by repeating the pulse with a period, fundamental period, equal to capital T0. So we have m from minus infinity to plus infinity, p of t minus m t0, and also let us choose t0 to be greater than t0. Okay, so x of t therefore will be the following periodic signal. So this is x of t. We are going to have the periodic extension of p of t. So this is minus t0 over 2 to t0 over 2. The peak value is a, and this is capital T0. So this point is capital T0 plus T0 over 2, and this point is capital T0 minus T0 over 2, and again the peak value is a. So we have the repetition of this pulse with a period capital T0. Now, in order to evaluate the Fourier coefficients of x of t, we can use direct integration, but in that approach, we have to use integration by parts, so the calculation of the Fourier coefficients is rather lengthy. But let us use the differentiation property of the Fourier series, how we obtain the Fourier coefficients of the derivative of a periodic signal. So, for instance, we can show the Fourier coefficients of x of t by ak. Okay, what is the derivative of x of t? So dx of t by dt will be okay, we are going to evaluate the derivative. So here we have a positive slope and then a negative slope. So we are going to obtain the positive value, and we are going to obtain a pulse. And here we are going to obtain a pulse with a negative magnitude. So, and we have the periodic repetition, of course, at t0. We will have also the pulse and the pulse with the negative value. Okay, the slope here is 2a over t0. So the magnitude of the pulse here is, okay, let us move this to, let me show it in a shorter notation as x prime of t as the derivative. So it is 2a over t0, and here we have minus 2a over t0. Okay, and we know that x prime of t, the derivative of x of t, is also periodic with Fourier coefficients j, k, omega 0, ak by the differentiation property of the Fourier series. Now, if we evaluate the derivative one more time, we are going to obtain impulses as follows. So the second derivative of x of t will be the following. Now, as you see, at minus t0 over 2, the derivative of x of t jumps to the value 2a over t0. And this jump, when we evaluate the derivative, is represented by an impulse with which is located at minus t0 over 2 with strength 2a over t0. Okay? Then we have a jump from 2a over t0 at t equal to 0. We have a jump from 2a over t0 to minus 2a over t0. So we have a jump, but it is negative now. So we have another impulse here with located at 0 with strength minus 4a over t0, and then again at t0 over 2, so this point here is t0 over 2 and this point is minus t0 over 2. Again at t0 over 2 we have a jump from the negative value minus 2a over t0 to 0, so it is a positive jump, and therefore we have again an impulse with strength 2a over t0. Okay, and we know that the Fourier coefficients of the second derivative of x of t will be jk omega 0 squared ak. Okay, now we have not completed the solution of the problem because our aim is to find the Fourier coefficients of x of t. But we are going to obtain the Fourier coefficients starting from the second derivative. Then we are going to obtain the Fourier coefficients of the first derivative, and then we are going to obtain the Fourier coefficients of x of t. But now we ask the following question. Now we remember the theorem, the statement of the theorem. The statement of the theorem is as follows. If a periodic signal is absolutely integrable in the Riemann sense over a period, then the Fourier coefficients tend to 0 as k tends to plus or minus infinity. So now if we look at these three periodic signals, starting with x of t, then its derivative, and then its second derivative. Of course, the first two signals, that means x of t and x prime of t, are absolutely integrable over a period. Okay, we see that over a period we only integrate this triangular paths, and it's absolutely integrable. And here also, in the first derivative, absolutely the condition of absolute integrability holds. But if we look at the second derivative, here we have impulses. And if we remember the previous example, for a periodic signal composed of impulses, the statements of the theorem is not valid anymore. Therefore, we do not observe the decay behavior in the Fourier series coefficients as k gets larger values in magnitude. However, it is very easy to evaluate the Fourier series coefficients of the second derivative, and then, obviously, once we evaluate the Fourier series coefficients of the second derivative, the AKs can be evaluated just by division by jk omega 0 squared. Of course, for k different from 0. For k equal to 0, we have to calculate a0 by using the straightforward integration formula. Okay, so next let us perform these calculations. Okay, now let us continue. Now, the second derivative of x of t, which is represented by this double prime, is also periodic. Let us call the coefficients bk. Right? Bk e to j k omega 0 t, k running from minus infinity to plus infinity. Now, how can we calculate the coefficients bk? So bk is equal to 1 over t0 from minus t0 over 2 to t0 over 2. Now here in this interval we have three impulses. The impulse with strength 2a over t0 at minus t0 over 2. Then we have the impulse at t equal to 0, which has a negative strength. So we have minus 4a over t0 delta of t. Then we have again another impulse at t0 over 2 with positive strength 2a over t0 delta of t minus t0 over 2 e to minus jk omega 0 t integrated with respect to t. Now, this expression can be calculated very easily by using the sampling property of the impulse. So it is okay. 2a over t0 times small t0, capital T0 times small t0 can be taken outside the integral, then we have the following: e to jk omega 0 t0 over 2. So we sample, the impulse samples this complex exponential term at t equal to t0 minus t0 over 2. So we have plus in the exponent. And then we have minus 2, okay, plus e2 minus jk omega 0 t0 over 2. Okay, so this expression gives us the expression of the Fourier series coefficients of the second derivative of x of t. In fact, we can simplify this as follows: 2a over t0 times small t0. Then we have 2 cosine k omega 0 t0 over 2 minus 2. In fact, we can take this 2 also outside the expression as the common term. So bk is equal to 4a over t0 times capital T0 times small t0 cosine k omega 0 t0 over 2 minus 1. Okay, so this expression is the Fourier series coefficients of the is the expression for the Fourier series coefficients bk of the second derivative of x of t. Now again, here we see that k appears only within the cosine function here, and therefore we do not observe the decay behavior given in the statement of the theorem. But this is expected because the second derivative of x of t contains impulses, and when we have impulses, in fact, although we calculate the Fourier series coefficients, we get a divergent expression for the Fourier series. But still, we are able to use these coefficients, although the series is divergent. We are able to use the coefficients to obtain or calculate the coefficients of the first derivative and the second derivative. Now, from bk, we can obtain ak, the Fourier series coefficients of the signal x of t, just by the following expression: bk divided by jk omega 0 squared, or bk divided by j squared is minus 1 minus k omega squared. Now, therefore, we can write ak as follows. It is 4a divided by t0, capital T0 times small t0, cosine k omega 0 t0 over 2 minus 1 divided by minus k omega 0 squared. Now here we observe that for larger values of k, ak is proportional to in magnitude proportional to 1 over k squared. So in this case, the coefficients tend to 0 as k tends to plus or minus infinity. The coefficients tend to 0 in the form 1 over k squared. So we have an even more rapid convergence in this case, or convergence to 0 of the Fourier coefficients. Okay, and of course we can also look at the Fourier series coefficients of the first derivative. The first derivative of this particular signal in our example also satisfies the conditions in the given in the statement of the theorem, and there we will see that the coefficients will have the term 1 over jk omega 0 as multiplier. In other words, bk divided by jk omega 0 will be the Fourier series coefficients of the first derivative of x of t, and obviously in that case as well, the first derivative also satisfies the conditions given in the theorem. The coefficients, the Fourier series coefficients tend to 0 in magnitude as k tends to plus or minus infinity. Okay, so the next step is, after all these discussions, now we have a feeling about the given theorem, which is the main topic in this video. So we are now ready to see the proof of that theorem. Okay, now in order to give a proof of our theorem, which is the theorem related to the behavior of the Fourier series coefficients, we have to see an important result known as the Riemann-Lebesgue Lemma, an important result in the theory of Fourier series. So let us see that result first. Riemann-Lebesgue Lemma. Now this lemma tells us the following. Let f be an absolutely integrable and here integrability is in the Riemann sense, in the Riemann sense. Okay, let f be an absolutely integrable function over the interval AB. Then the statement of the Riemann-Lebesgue lemma, limit as omega tends to infinity, the integral of f of t sine omega t is 0. So as omega tends to infinity, that means omega here is the angular frequency of the sine function given in the integrand, and f of t is multiplied by that sine function. The integral is equal to or tends to 0 as omega tends to infinity. Now, we are going to see the proof of this lemma in a minute, but it is very easy to understand the meaning of this statement. In fact, the integrand, if we look at the integrand carefully, it is the product of f of t with sine omega t. So in fact, it is a modulated signal, a certain function multiplied by a sinusoidal function, which is sine omega t. But we will see that in the lemma, we can replace this by cosine or e to j omega t if you wish. The result will be the same. So for higher frequencies, as omega tends to infinity, as omega gets larger and larger, of course these in the evaluation of the integral, the areas corresponding to positive portions and negative portions will tend to cancel out. And for higher and higher frequencies, this will be, the result will be observed more closely. The result will be very close to zero. The result of the integral will be close to zero for larger values of omega because of this, the fact that this integral is the integral of a modulated, amplitude modulated function, in fact. Okay, so let us see the proof. Now, for the proof, we will start with the simplest possible case, and then we are going to build up the steps. Okay, the first step in the proof is, let us assume that f of t is the constant function over ab. So let f of t be equal to c, where c is a constant. Okay, for t between a and b. Okay, then the integral of this f of t times sine omega t will be the integral of the constant times sine omega t integrated with respect to t. So this will be equal to c minus cosine omega t divided by omega and this expression evaluated at the integration limits a and b. Okay? Now, since cosine omega t is bounded between -1 and +1 for all values of t, it is clear that this will tend to 0 as omega tends to infinity. Okay, for this simple case. Now, the second step in the proof will be the following. Let us assume that f of t is piecewise constant over this interval. So, let the interval I, which is the interval AB, be decomposed to subintervals. We mean the following here. This is A and this is B. So this is our original interval AB. So the subintervals are, for example, this is I1, this interval here is I2, and finally we have IN. subintervals I1, I2, In such that the union is the interval I. And let f of t be equal to I from 1 to n fi of t, where fi of t is equal to a constant over the interval I sub I and 0 elsewhere. So where fi of t is constant over I and 0 otherwise. Okay. Now the integral, of course, of f of t multiplied by sine omega t integrated with respect to t can be decomposed as, and of course, since we have a finite sum, we can write it in the following form: I from 1 to n okay, this is sine omega t. Okay, I from 1 to n, from a to b, fi of t sine omega t integrated with respect to t. But fi of t is equal to a constant over the corresponding interval I and 0 outside that interval. Therefore, we can also conclude that this goes to 0. Just by using the previous step, we are able to decompose the integral over integrals over each subinterval, and obviously this integral will tend to 0 as omega tends to infinity. Okay, so for the piecewise constant case, here f of t is, in this case, is piecewise constant. And we are able to also conclude that the integral tends to 0 as omega tends to infinity. Okay, now what happens for the general case? Then we are now ready to discuss the general case. Okay, now we are ready to discuss the general case. We are going to call this case 3. So it will be the general case. Okay, so we have an arbitrary, absolutely Riemann integrable function over the interval AB. So let f be an absolutely integrable of course in Riemann sense, function over the interval AB. Now, in order to prove the statement of the Riemann-Lebesgue lemma for this f, we are going to follow the following steps. First of all, we are going to approximate this f by a piecewise constant function over the interval AB. And we know from the previous case, case 2, that the statement of the Riemann-Lebesgue lemma holds for this piecewise constant function. So the idea is roughly this. So given an epsilon greater than 0, we can find a piecewise constant function let us call this f cap of t over the interval AB, such that the integral from a to b magnitude of f of t minus f cap of t integrated with respect to t is less than epsilon over 2. So this is the more rigorous way of saying that we are able to find a piecewise constant function which is arbitrarily close to f of t in this sense, given by means of this integral expression. It is very easy to justify this because, as we remember the steps of Riemann integration, in Riemann integration we consider the upper and lower Riemann sums to approximate the integral. And in fact, these upper and lower Riemann sums are calculated in terms of piecewise constant functions approximating the original function, whose integral we are trying to compute. Therefore, for any absolutely integrable function, we are able to find a piecewise constant function arbitrarily close to that function. Now, how do we use this result to prove our Riemann-Lebesgue lemma in the most general sense? Now, consider the integral, or rather the magnitude of the integral. Consider the magnitude of the integral we are trying to evaluate, from a to b, f of t sine omega t integrated with respect to t. Okay. Now the trick is the following. We are going to add and subtract f cap of t. Okay, and this is therefore equal to, from a to b, f of t minus f cap of t plus f cap of t, then multiplied by sine omega t and integrated. We are considering the magnitude of this integral. Okay, now we can write this as using the linearity of integration operation. We are able to decompose this as f of t minus f cap of t, okay, multiplied by sine omega t, integrated with respect to t. Okay, this is one integral, and the other one is from a to b, f cap of t sine omega t integrated with respect to t. Okay, we have the magnitude of this overall expression. Now, by using triangle inequality, let us continue, okay, over there. Okay, this, okay, let us continue here. This is less than or equal to magnitude of the integral from a to b, f of t minus f cap of t sine omega t integrated with respect to t, plus magnitude of the integral f cap of t sine omega t integrated with respect to t. Okay, so we have as an upper bound to this original expression, we have this expression as a whole. Now let us call the first part the first expression, or expression 1, and let us call this expression 2. Now first let us look at expression 1. Okay, expression 1 is this: from a to b, the integral of f of t minus f cap of t multiplied by sine omega t integrated. Okay, this is less than or equal to integral of magnitude of f of t minus f cap of t. Then we have magnitude of sine omega t integrated with respect to t. But we know that sine omega t is always less than or equal to 1 in magnitude. Therefore, expression 1 ends up with this expression. Okay. Therefore, this is less than or equal to, eventually, from a to b, magnitude of f of t minus f cap of t integrated with respect to t. But at the beginning of the proof of the general case, case 3, we have chosen this f cap of t for a given epsilon. For a given epsilon, we are able to find an f cap of t such that this expression is less than epsilon over 2. Okay? Therefore, expression 1 is less than epsilon over 2. Now, what about the second expression? Expression 2. Expression 2 is, we have the piecewise constant function f cap of t sine omega t multiplied by sine omega t and integrated. Okay, so what can we say about this case? Now, for expression 2, we can do the following. Since we know that from case 2, since f cap of t is piecewise constant, the Riemann-Lebesgue lemma holds, and therefore for the given epsilon, we can find omega 0 such that this is less than epsilon over 2 for omega greater than omega 0. Okay, this is a rigorous way of telling that Riemann-Lebesgue lemma holds for the piecewise constant function f cap of t. Now, combining these two expressions, okay, combine the two expressions. So given any epsilon greater than 0, we are able to show that from a to b, the magnitude of the integral f of t sine omega t is multiplied by dt is less than epsilon for omega greater than omega 0. So this proves the general case. Since epsilon is arbitrary, it is greater than 0 but arbitrary, and it is given at the beginning of the proof. So corresponding to that epsilon, we are able to find the piecewise constant function which satisfies the initial statement that the original absolutely integrable function is approximated by f cap of t. And then we also apply, for the same given epsilon, we are able to find an omega 0 frequency such that when the frequency omega is greater than omega 0, the Riemann-Lebesgue lemma holds, and therefore this can be made less than, the expression can be made less than epsilon over 2. And if we combine the two expressions, we get the proof of the general case. Okay, now we are ready to use Riemann-Lebesgue lemma in our theorem related to the behavior of the Fourier coefficients of a periodic function which is absolutely integrable over a period. Okay, so our next aim will be to study this problem. Okay, now the last step will be to remember our original theorem given at the beginning of this video and how we use the Riemann-Lebesgue lemma to prove it. Now, first of all, the Riemann-Lebesgue lemma was given in terms of the sine function, but it is also valid for cosine or the complex exponential functions as well. So let us remember the Riemann-Lebesgue lemma. We have a function f is absolutely integrable over the interval AB. So we have the following limit as omega tends to infinity from a to b, f of t sine omega t integrated with respect to t is 0. But as you see, sine can be replaced by cosine omega t or e to j omega t. We obtain the same result. So let us also note this down. Sine omega t can be replaced by cosine omega t or by e to j omega t, because e to j omega t is just cosine omega t plus j times sine omega t. We are going to obtain the same result. Now, for the Fourier coefficients, remember the statement of our theorem. We have a periodic signal, periodic function, which is absolutely integrable over a period. And we have two statements related to the coefficients. The coefficients are bounded in magnitude, and they in magnitude tend to 0 as k in magnitude tends to infinity. Okay? Therefore, in order to apply Riemann-Lebesgue Lemma, we just remember our original problem. Now let x of t be a periodic function which is absolutely integrable over a period. Okay. Then our theorem tells us the following two statements. The Fourier coefficients in magnitude are bounded for all k. And second, magnitude ak tends to 0 as magnitude k tends to infinity. So k may tend to plus infinity or minus infinity. So we have these two statements. Now for the first statement, of course, this is quite straightforward because ak is equal to 1 over t0 from t0 to t0 plus capital T0 x of t e to minus jk omega 0 t integrated with respect to t. Now magnitude ak is 1 over t0, magnitude of this integral x of t e to minus jk omega 0 t integrated with respect to t, but this is less than or equal to 1 over t0 from t0 to t0 plus capital T0 magnitude of x of t integrated with respect to t, because magnitude of this e to minus jk omega 0 t is equal to 1. And obviously, since x of t is absolutely integrable over a period, this is finite. And therefore it is bounded by an upper bound. Therefore, all AKs are bounded. So this is a rather simple proof of this fact. If x of t is absolutely integrable over a period, then AKs are all bounded in magnitude for all k. So this is the proof of the first part. So in fact, we are doing a simple proof of this original theorem. The proof of the second part is by Riemann-Lebesgue Lemma, by Riemann-Lebesgue Lemma. If you look at AK, which is equal to 1 over T0, from T0 to T0 plus capital T0 x of t e to minus jk omega 0 t integrated with respect to t by Riemann-Lebesgue Lemma, it is clear that we have the form of the integral we have used in Riemann-Lebesgue Lemma. But instead of sign, now we have the complex exponential, but we have seen that for the complex exponential multiplier as well, the result is valid. And by Riemann-Lebesgue Lemma, it is clear that this expression goes to 0 as magnitude k tends to infinity. K tends to plus or minus infinity. Because we are going to observe a complex exponential multiplier with a very high frequency when k gets larger in magnitude. And in that case, remember the simple interpretation of Riemann-Lebesgue Lemma, the positive and negative areas in the computation of the integral will tend to cancel out because of these rapid oscillations and the modulation of x of t by means of that multiplication by the rapidly oscillating sinusoidal functions. By Riemann-Lebesgue Lemma, ak will tend to 0 as magnitude k tends to infinity. So this is the formal proof of this well-known result in the theory of Fourier series. So thanks for watching.